What if I told you there's a technology that can literally see the future? A tool that lets you stop a disaster before it even has a chance to start? Well, that's exactly what we're talking about today. We're diving into the incredible science of thermography, which is all about seeing failures in our most critical industrial equipment long before they happen.
I mean, really think about that for a second. What if you could stop a fire before it ever started? It sounds like something out of science fiction, right? But in the high stakes world of industry, power plants, massive factories, the data centers that run our lives, this is not some hypothetical question. It is the daily challenge. Preventing catastrophic failure is job number one.
And the key to preventing those failures, it all lies in seeing what other people can't. Now, if you look at a thermal image, you might just see a bunch of cool, colorful patterns. But a trained thermographer, well, they see something completely different. They aren't a photographer. They're more like a detective, reading this invisible language of heat to find a final critical warning sign.
To really get what they do, we've got to see the world the way they do. We're on the hunt for invisible threats, these constant hidden forces of physics that are, at this very moment, trying to break our most important systems. It all boils down to a pretty simple principle, actually. Industrial systems run on just massive amounts of energy, but a tiny fraction of that energy is always lost as waste heat. Now, when a component starts to fail, whether that's electricity struggling to push through a bad connection or parts rubbing together with too much friction, it generates extra heat. That unwanted hotspot is the very first clue, the crucial signal that something is going wrong. But here's the catch. Finding that clue isn't easy. Not at all. It's a hunt, a real hunt for a very specific signal of failure. And it has to be found in an environment that is just full of thermal interference or chaos.
So let's define our terms. The thermal signal is the pure, real heat being generated by the fault itself. Just think of it like evidence at a crime scene. It's the heat created by a loose electrical wire or a failing bearing. That signal, that's the truth we're after.
But here's the problem. The world is full of other heat sources, and we call all that stuff thermal noise. This is all the reflected heat from the sun, the cooling effect of the wind, even heat bouncing off other equipment nearby. This noise, it can completely drown out, or even worse, fake the signal that we're desperately trying to find. And this really breaks it down perfectly. The signal, that's what's happening inside the machine. High resistance, friction, you name it. The noise, on the other hand, is everything happening to the machine from the outside. The sun beating down on it, wind blowing across it. The thermographer's entire job is to somehow filter out all that noise to find the one true signal. So how in the world do they do it? This is where the real science, the real detective work comes into play. Thermographers have a whole toolkit of techniques they use to fight back against the noise and get to the truth. Okay, for example, take a shiny metal surface. It basically acts like a thermal mirror, right? It just reflects all the noisy heat from around it, completely hiding its actual temperature. The solution? It's brilliantly simple. You just apply a piece of non-shiny matte electrical tape to it, and suddenly that little spot stops being a mirror and starts broadcasting its true temperature, loud and clear. You've just turned up the volume on the signal. And it's not just about the surface, it's also about the conditions. You can't just do an inspection whenever you want. If the equipment isn't running hard enough, say below 40% load, a fault might not even generate enough heat to be spotted. Too much wind? Poof! It'll just blow the heat away, hiding the signal. And oh man, inspecting in direct sunlight is a rookie mistake. The sun's heat will just overwhelm everything. You have to wait for those pre-dawn hours or find a shady spot. So once you've managed to control all that noise, you can finally start decoding the signals. And what's fascinating is that different kinds of failures create their own unique thermal patterns, their own signatures. Now, for electrical systems, the most important measurement is something called delta T, or temperature difference. See, it doesn't really matter if a connection is 50 degrees or 100 degrees by itself. What truly matters is how much hotter it is than an identical, healthy connection right next to it. That comparison gives you context. And as this chart shows, a difference of just 4 to 15 degrees Celsius, that's a probable problem that needs to get on the repair schedule, like now. But if that temperature difference climbs over 40 degrees Celsius, whoa, that is not a warning anymore. That is a 5-alarm fire. It means failure is right around the corner, and the system needs to be shut down immediately for emergency repairs. This is the difference between a planned fix and a catastrophic business-ending outage. And here's a perfect example of how you decode these different signals.
A steam trap can fail in two main ways. If it's leaking, it shows up as uniformly hot. That's a problem for sure. It's wasting a ton of energy and money. But if it's blocked, it actually shows up as cold. And here's the critical insight. That cold, blocked trap is the real safety hazard. Trapped water can cause something called a water hammer that can literally blow pipes apart. So the less obvious signal, it points to the much greater danger.
Okay, so you've found the signal, you've decoded it, but the job's not done. A thermal image all by itself is just a pretty picture. To make it useful, to make it mean something, it has to become actionable data. For a thermal image to have any real value, it has to be part of an auditable report. You need all this extra info, this metadata. What exactly was the load on the machine? What was the wind speed? What were the camera settings? Without all this context, you can't prove your finding is real. You can't track it over time. It's not data. It's just an anecdote. See, it's not just about finding problems. It's about creating a rigorous, defensible record. This audit trail is proof that you did your due diligence, which is absolutely critical for safety, for regulations, and for insurance. This is what turns thermography from a cool trick into a cornerstone of industrial reliability. Ultimately, this whole science is really about one thing: listening. It's about training yourself to see the subtle signals of failure that are hidden in plain sight all around us, all the time. It really makes you wonder, doesn't it? What other critical warnings are being broadcast every single day, just waiting for someone to tune in and listen?